morning, everyone. My name is William Chang, and my student ID is 0362652, and I'm from Section 3 Group 2022. Today, me and my teammate will be discussing how data mining technique can be applied to analyze this dataset with a focus on classification, clustering, and anomaly detection. This technique can allow us to extract meaningful insight from this dataset. So, first one, we use classification. We use classification to predicting fentanyl involvement. Fentanyl is a key contributor to overdose death, but identifying fentanyl involved case can be challenging and complex. Using a random forest classifier, we can analyze demographic pattern or other factor to predict whatever fentanyl is involved in an overdose case. Second, we use clustering. So we use clustering to identify poly-drug use pattern. Overdose often involve multiple systems in this dataset, but finding pattern in drug combination is very complex. We're using chemical clustering group tests based on drug mission help us to identify common poly-drug use trends. This insight allows for target harm reduction strategy and better intervention program through this clustering data mining technique. Last one, we use anomaly detection to identify unusual overdose cases. So some overdose cases don't follow us expected pattern, such as unusual exclude or red drug combination. We don't know. So we use isolation forest anomaly detection help us to identify this outlier. So we can enabling and lead intervention and quicker respond to emerging drug threats. So now me and my teammate will demo each technique one by one. Check it out.
Thank you, William, for setting out the problem statement and the objective. So my name is EB, and my student ID is 36379. And I'll be carrying out the following part of the coding part. So I'll first start off by importing the library we are going to use. So the first library we are using is the Panda, so we import Pandas SPD, and the next one will be the NAPI, so we import NAPI SMP. And continuing, we will import Matplotlib, the pilot SPLT for the figure diagram, and we will import Seaport SSNS. Now for this part is for machine learning and pre-processing part. So for this, we will take it from sklearn model selection and import trend test split and also the cross-val score. And the next one will be from sklearn.ensemble and import random forest classifier for classification and isolation forest. The next one will be from sklearn.cluster and import k-means. And this is for clustering. And now we will be importing sklearn.pre-processing and import robust scalar. There is an error here, pre-processing. And import scalar. So now we will take it from sklearn import, but we're not using standard scalar, but instead of it we use robust scalar. And the next one will be from imvlearn.oversampling, but we're not import random oversampler. Instead of it is smooth. Okay, so this is a part for the machine learning and pre-processing. So now we move on to the model evaluation metrics. Sorry, it is quite noisy out there. So from sklearn metrics, we will import. What will we import? We will import classification report, confusion metrics display, ROC curve, AUC, and C-hot score, Davis Bovin score, and Kalinski ups score. So this is all for the metrics. Now I'll be moving on to the first actual step, which is loading the data step. So we'll take a file from the file path from the accidental drug-related death clean final CSV. Yes. And df equals to pd.read CSV. Okay, so now pd.read CSV and bracket file path. So we will convert our y and n, which is a yes and no, in the substance columns to a binary form into 1 and 0. Yeah. Next, we'll let the substance. We will choose the substance that we wanted to use here. So we have a bunch of substance. So for the time purpose, I will just copy and paste the drugs that we've chosen here. So what we have here is heroin, cocaine, fentanyl analog, oxycodone, oxymorphone, ethanol, hydrocodone, benzodiazepine, methadone, meth or amphetamine, amphet, tramet, hydromorphone, morphine, that is not heroin, xylazine, gabapentin, opioid, NOS, heroin or moth or codeine, and other opioid. So these are the substances that we've chosen to convert the yes and no in the substance columns to binary 0 or 1. And now we will need to make sure that only the existing substance columns are processed. So before this, I'll label it here. So we will let the existing substances equals to df.columns.intersection of bracket substances. And for the column in existing substances, we will let df bracket column equals to df bracket column dot map bracket lambda x equals 1 if x equals y instead of yes, because we're using y in the dataset, L0. Okay, so now we move on to the next one. Now we will be creating a new column counting the total number of substances involving in each case. So we'll let df brackets substance count equals to df.columns.intersection. No, we'll let df equals. So now we'll let df bracket substance count and equals to df bracket existing substances dot sum, and axis is equals to 1. And now we will need to select the feature columns for classification that we will be using later. So we're choosing encoded columns that is equal to bracket the encoded value. We have age, race encoded, and sex encoded, and the last one, ethnicity encoded. So the existing encoded columns will equal to df.columns intersection the encoded columns. So move on, we will need to define feature X and target Y for the classification techniques. And so our X will be equaling to df existing encoded columns plus a list of existing substances. So now our X will be equaling to df existing encoded column, but we will need to put a bracket here because we need to add something behind it. So plus a list of existing substances and here and dot drop bracket columns equal to, here we will choose fentanyl as for the classifications. And if there's any errors, we will ignore it. So yeah, so next we will let our Y equals to df. Here, as we said, we choose fentanyl. And if fentanyl, then df.columns, else none. Okay, so now we need to ensure the target column is exist. So if Y is none, okay, we will raise an key error and stating that the target column fentanyl is not found in the dataset. Yeah. Now we'll be handling the missing value by filling with the median values. So X field will be equal to X dot field and a X dot median bracket. So this is the data preprocessing part before we start any data mining techniques such as anomaly detection, classification, or clustering. So this tree is the one that we chose, and I'll be passing it to my teammate to continue the continuous technique.
I'm moving on. I will focus on anomaly detection by using isolation force algorithm. So for step 1, we need to apply the isolation force. But first, we assume that there is 2% of the data that contains anomaly, so we just put 2% here, random status 42, and assign outliers. So in step 2, we will need to remove the outliers. So we remove rows where the model identified anomalies. So in step 3, we need to add a column of the anomaly in our datasets for visualization later. Labels for visualization. So on step 4 onward, we need to evaluate and validate our anomaly detection models with the scatter plots and also counting on how many anomalized cases and normal cases. Step 4, visualization with using scatter plot. So in X with H, Y with substances. So in here, we assign blue color as the normal cases, while the red color as the normalized cases. In title here, we shows that this is anomaly detection isolation force. The titles anomaly as normal. So these scatter plots will show normal cases in blue and detected anomalies in red. So next step, we need to count the detected anomalies. Step 5. Detected anomalies. Last step, print all the results. So now we're going to run this application to see the results. Okay, seems like there's something wrong with it. We'll rerun it. So there's something wrong. So we have solved the problems already, so it should be work. Okay, yes, the output is already there, so we can view on the scatter plots first. So as we can see, the blue color dots represent the normal cases, and red color dots represent the normalized. So we can see there's very high substance and caustic content, the normalized. And then also in age distributions, there's some unusual normalized, which included there is some young age and also an old age. And for the normalized detection, as we can see, there's out of 11,981 data points, isolation first detected almost 240, which is 2%, exactly 2% as per our contamination setting. And this means our model correctly identifying potential outliers without removing too much data. So the remain normal cases is around 11,741. So if a normalized are truly incorrect or unusual cases, it can distort predictions. By removing them, we expect the model to generalize better. So next, we continue on the classifications.
Hi, my name is William. So I want to demo the classification part, demo the coding part. So let's go to it. So let's go for the first one. Let's use the smart data to data balancing. Yeah, let's technical first. Step 4. Data balancing with smart. Yeah, the smart. Equal smart. When the GRP22. Yeah, yes. Okay, then smart coffee, pretty as strengthening and white strengthening. So why we need to use the smart here, because smart helps us to generate this sample for the minority class. Yeah. So in the fit sample, it helps us to class a balanced data set. So let's go move on to the step 5 to train the text split. Step 5. Train text split. Right. So why we need to train the test split, because we need to split the balanced data set into the training to 70% and testing for 30%. So the render step to 42 to ensure the reproducibility of the data set or during the run call. Then move on to the step 6, training the random forest model using the classification. So step 6. Classification using random forest. Good. Input. Forest. Model. And white train. Oh, sorry. Stop. So why we need to choose a random forest, because random for model is an example learning model to using the multiple decision tree, and we set to an estimate to 200 because it will create 200 decision tree, and max step 10 to limit the depth of the tree to avoid overfitting, and the class weight is balanced because it will help us to handle any remaining balance. Yeah. So let's move on. Let's go to the predict test split. I type the code first. Predict test set. Sorry, it's predict test set. So predict test set. Why? Equal RF model, predict as test. And also go to the step 7. To classification model evaluation. We need to train the performance. Sorry, it's not this one. It's a shortcut. I thought it's this one. And classification. And also Setup. Classification report as there. Okay. So I explained this two code. After training, we need to predict the label for the test set, the classification report, or provide the metric like position, recall, and advanced score to make sure the model performance is stable and have some result to tell us this model is stable or not. So let's go to the confusion matrix. Confusion matrix visualization. This time we need to visualize the plot. CM confusion matrix y test y correct. ESP sorry. ISP confusion metric display confusion metric equal CM. Also TSP plot display the plot, and we need to set in the color into the green. Set into the green. Reduce format D and to show the plot. We choose the confusion metric visualization here because the confusion metric shows the correct and incorrect prediction, and the diagonal represent correct prediction, and off diagonal element indicate misclassification. So let's move on into step 6 to get the feature important plot. Get feature important plot feature underscore important sorted IDS MP dot underscore feature display the plot feature plot. Setting the size of the plot, we need to drop 6. 12 and 6, yeah. Plot linking setting to the center. Right. Let's time column. Okay. And yes. Rotation we set to the 45, and touch we set to the right. Yes. Rotate the table. Rotate the labels. Add the Y label. It's important. So feature important. And yeah. So the feature important file we need to use the feature important because it tells us which variable influence the prediction the most, and it will help in feature selection and model integration. Let's move on to the ROC curve and the matrix. Step 7. OC curve and the line. Taking the best test. Okay. Sorry. Here best test claim by class. OC. AUC. Also, setting the fixed side into setting MCs. Always setting to the blue. Table we set to add. Now give the label. Now we need to name the label. S label is also positive ref, and the Y label is two positive ref, and the title of the plot also with the box. Also color order. short plot. So why we need to use RLC? Because the RLC, the full name of the RLC is received operating characteristic, curve evaluate model, performance across the different three cores. AUC area under curve, measure overall performance, the closer to the one is the most better. So go to the step at cross validation. Starting is F1. F1. What is scope? Scope. Also. Scope. Scope. So in cross validation part, cross validation ensure the model is generally well. We use 5-fold cross validation to calculate F1 scope as a multiple subset. For the code that we take just now, we have a quick look. The step 4 is data balancing, trend test split, classification using the random forest, ready test steps, based classification, model evaluation, confusion matrix visualization to generate the plot, and get the feature importance under the plot, and the RLC, and also the cross validation F1 scope. So let's run the code. So in this demo, we analyze the classification report and cross validation results to evaluate our model performance. The classification report shows on overall accuracy is 73%. You can see here 73%. Which position and recall metric highlight the class. One have recall, F1 scope, have recall 66%, here 66% here, and this means some specific case missed. The F1 scope indicate the balance performance. Improvement could be met through parameter turning out of or feature selection. Our cross validation F1 scope range for 0.73 to 83 in here, the cross validation F1 scope, and our mean F1 scope is 0.77. So confirming this, the model generate well performance across different data set. So this is the confusion metric model performance evaluation. Now let's evaluate the model performance using a confusion metric. This metric shows how well our classification model predicting orbital space. So in the true positive, which here 1582 is a correctly identified orbital cases. So in true negative, which here is most higher 1887 is surely correctly identified non-orbital case. So for the false negative here 450 is a model incorrect predict orbital when it was not. So let's go to the last one, which is the false negative Fn at 803 model miss actual orbital case interpretation. Let's go to the interpretation part. The model performed well with more correct classification than incorrect ones. However, the false negative rate 803 cases suggests that the model misses some high risk case, which could be improved by turning hyperparameter or using more features. Overall, the model provides valuable insight for the orbital risk prediction. Let's move on to the another one, which is the feature importance. Let's use a random forest model to determine which factors are more important in predicting orbital risk. So sectors like here, which you can see here, Pentaine, heroin, and benzodiazepines and jondiazepines have the highest feature importance, meaning they play a significant role in orbital cases. Demographic features like age and location also contribute to the risk assessment. Why is this matter? We use this because identify key predictors help in targeted intervention, such as creating awareness program for high-risk system. So let's go to the last one, which is the random forest classifier, which is this one. So now let's evaluate our classification model, the receiver operating characteristic ROC curve, which shows how well the model distinguishes between high risk and low risk case. So the AUC here, you can see here is 0.82, is indicated that our model performs very well. AUC value equals to 1 is indicate better performance. So here we have 0.82 is very nearest. So well, 0.5 will suggest random casting. So in interpretation, this means our model has a strong ability to identify high risk drug combination, which could help prevent overdose.
The clustering using K-mean. So step at clustering using K-means. Yeah. So here we use robust scalar instead of standard scalar because the standard scalar performance is a bit low. So we choose robust scalar because it performs better. And here we use an X scale equals to our scalar fit transform with the bracket of X clean. And now we need to use the elbow method for optimal K. And here we will take the inertia equals to an empty bracket. And OK range, here we will take a range of 2 and 10. That's enough. So for K in K range, our K means will equals to K means bracket and cluster, and our random state we choose 42, and our n integer, and not integer, n in it will be 10 here, and our K means of fit bracket scale and inertia dot append, and bracket K means start inertia. So this is our part for the K in K range. So now I will plot the graph out after the clustering. So this part will be the plotting the elbow method graph. Sorry, it should be O here. And here we will use the PLT figure, and our figure size I will choose 8 and 6 here. Yeah. So the next one will be PLT dot plot bracket K range inertia and also marker equals to bracket O And our line style, we'll be choosing a dash. That's enough. Yep. So the next one, for our X label, PLT.X label, which is the title for the X-axis, will be the number of cluster K. It should be a dot, sorry. And the next one will be our PLT.Y label, which is our Y-axis, should be inertia. And our diagram title, we will make it as the elbow method for optimal K. And we have the PLT X6, and bracket K range. So the last two one, we will need to show the diagram out. PLT touchstone. Yes. So, and then now we need to train our best K-means model that we assume our K equals to 4. Our best K-means here will equals to K-means, and our N cluster we will choose 4, random state 42, and init 10 as usual. So our best K-means, our best cluster, sorry, will equals to best underscore K-means fit predict X scale. So now we have our clustering evaluation matrix. And now we will need to print out all our outcome that we have trained up here for the elbow method and our best K-mean model. So yeah. So I will just print it out. Clustering evaluation matrix. So this is the title for the first one. And then I will print the Sehot or Simpot score. Yeah. I show you E. Which is the Sehot score of SQL and best clusters. So this one they will print out directly from this. And next, our Davis Odin score will equal to Davis Odin score, SQL, and also the best cluster. And the last one, we will be printing out the Kalinski. Sorry, Kalinski. Yeah. Harabas score will equal to Kalinski Harabas score with the SQL and the best clusters. So now I'll be running the whole file to show you the outcome of the clustering. So this is our clustering evaluation matrix for the silver score. What we got here is 0.642685, which is equivalent to 0.64. Yeah. And for the Davis Boolean score, we got 0.57, and for Kalinski Harabas score is 40100.1. So this is our outcome for the clustering evaluation matrix. And later, my teammate William will be explaining for the diagram part. So and the conclusion part. So thank you.
Let's move on to K-mean clustering eval method. So this is the graph or eval method for optimal K. This graph represents the eval method which help determine the optimal number of cluster K for K-mean clustering. The x-axis represent the number of cluster with 2 triple here, and the y-axis show the data which measure how well data point fit between cluster. So the key observation what we can see from this graph, this shadow in interact up to K equals 3 in here, K equals 3. After which the decrease slow down. You see the line slow decrease is down already. This suggests the 3 cluster is the best choice from here. So by applying K-mean with K equals 3, we can group different cases of strike data depth based on sustained combination with building common poly drug use method. Thank you, my roommate, to demonstration the coding part. So I am doing the conclusion right now. So in the conclusion, the code successfully apply classification and limitation and also the clustering technique to the dataset that we need to solving. So using the iteration for us, 2% of the data was identified as anomalies and removed. Well, small as well MOTE small balance the dataset to address class imbalance. A random forest classifier achieved strong performance as incident by the classification report. Confusion matrix and ROC curve with feature important analysis highlight key predictors. Clustering with K-mean identified 4 meaningful clusters. Validated by Sehot, Davis Boolean, and Kalinski Harabas score. Overall, the approach provides good insight into sustained use pattern and predictive factors for fantastic information in drug-related death dataset. So this is all about the report we do in group assignment 1. So thank you for watching and goodbye. Have a nice day.